Here we have an example of several Fourier transform pairs from the table in the book, and on the bottom left, several Fourier transform properties from the table in the book. On the right, we're looking at four different versions of a similar signal and their Fourier transform magnitudes. These examples illustrate several of the properties and how we go about using the properties to understand when we see something in a Fourier transform magnitude, what is it telling us about the time domain version of the signal, and vice versa. When we look at a time domain signal, such as those on the left, what does it tell us about the magnitude of the Fourier transform? This is one of the points of learning about the variety of transform pairs and properties. It makes the mathematics easier, it allows us to confirm our results are correct, but it also informs some intuition about how we look at signals and their transforms. What we have here is, on the left, a variety of 20 hertz cosine waves. And they are limited in time, and the signal is going to be considered zero everywhere outside of a limit in time that is symmetric around 0 seconds. So in this first example, we let the cosine wave exist for one period and then be zeroed out for all time. And then we do the Fourier transform of it, and we're showing the magnitude here. Then we do the same thing for increasing periods. So we see if we have 3 periods, 9 periods, and 27 periods, and we see what the Fourier transform is. Now, in all of these cases, we're only showing a limited amount of time, but the signal is zero for until negative infinity, until positive infinity on both sides. We're just not showing that in our graphs on the left. So let's take a look at applying a few of the properties here. So first of all, let's look at some pairs and properties. If we look at pair number 5, we see we have a rectangular pulse, and it gives us this sinc function in the Fourier domain. And we combine that with what is called the modulation property. So here we let x of t be a rectangular pulse that's going to exist and be on for 1, 3, 9, or 27 cycles of the cosine, and we modulate that x of t rectangular pulse with cosine of t, where omega naught represents a 20 hertz frequency. Now the modulation property tells us that we take the capital X, which is the Fourier transform of the signal x, which is this sinc function right here. And it says you take the complex values there and you shift them right in frequency by omega naught radians per second, and then you add that to a copy that's also shifted left by omega naught radians per second, and you average them. You take half. So we can see that that is actually what's happening right here in the Fourier transform of one cycle. We have a sinc function centered at negative 20 hertz and a sinc function centered at positive 20 hertz. And then we see the other cases are similar. We are adding together, per the modulation property, sinc functions at negative 20 and positive 20 hertz. And we can see the net magnitude. Now, as the number of cycles increase, we are letting this tau here get wider in the x of t signal. And we see as we let it get wider, tau increases and gets larger as we go to more periods. And as we do that, we go through the sinc function more quickly. So we have a dilation or a slowdown in the time domain, gives us this compression or acceleration in the frequency or Fourier domain. So we see here, in all cases, around positive 20 hertz, there is a sinc function, but it's getting narrower by a factor of 3 as we go down each row here, because this rectangular pulse that we were modulating by the cosine is getting wider. So this is a property that we often take advantage of and notice, is that when signals expand in the time domain, so as tau gets bigger here, it expands in the time domain, they compress or get tighter in the frequency domain. So when I see very tight things in the frequency domain, that tells me that I have some long-lasting or long-time feature in the time domain. Let's look at some of the other properties. We notice property 5, the frequency shift, says that if I take a rectangular a function's x of t, such as our rectangular window that is going to be 1 for the period that we're not zeroing out this signal, and I multiply it by a complex exponential, I get a frequency shifted version. We know that the cosine that we are actually multiplying the signal by here can be expressed as a sum of two complex exponentials using Euler's formula. So we get one at frequency positive omega, which gives us this shift to the right, which comes out here in the modulation property. And the cosine also includes a component at negative omega naught, which is subtracted, giving me plus omega naught right here in the modulation property. That description that we just discussed uses the linearity properties of the Fourier transform. Specifically, it uses the additive property. I was able to say that since the cosine is the sum of two complex exponentials, that if I want to understand what the Fourier transform of a signal involving the cosine is, I can consider it as the sum of two complex exponentials. And that also explains the modulation property. So all these properties are interrelated. They derive from the form of the Fourier transform and inverse Fourier transforms. Now, if we go down the list at the top, we see we have transform pair 8, which tells us if I have a cosine that goes on forever, that its Fourier transform has these two impulses in the Fourier domain. And we can see that by the time I get up to 27 periods, I am getting closer and closer to these sinc functions, giving me impulses. So these sinc functions are going to have area equal to 1 before the scaling here by pi, and they will get closer and closer to impulses at the 20 hertz and minus 20 hertz as I increase the number of cycles. We can see on the graph in my y-axis that my limit here, my upper limit is 0.03, then 0.08, 0.25, 0.7. The height is growing of these sinc functions is growing by a factor of 3 each time I expand in time by a factor of 3. So the total area under here, which is related to the energy, as we're soon going to see in Parsifal's theorem, the total area is increasing as I add more cycles. Now, you might be asking, if the energy is increasing, but I still have area 1 under here, that doesn't quite add up, because as I add more cycles, the energy is growing without bound, yet my area here is 1. The area is indeed converging to 1 in our graph on the right. However, remember the energy is based on the square of the voltage. And when you square an impulse, you no longer have an integrable function. That is beyond the scope of this lecture to prove it, but you can do that with various limit arguments, showing that, yes, I can integrate over an impulse, its area is 1, and it's finite, it converges even though the value goes to infinity. But if I take that same impulse and I square it, and this can be done with any of the approximation models that we discussed in the first couple of weeks of classes, you will see that the integrating over the square gives us, which is what you need to do for energy, you take the voltage squared, will give us a divergent integral. So that explains why this still all adds up. We have here the formula saying you will get impulses in the Fourier domain for a cosine that exists forever. To help test your understanding, I encourage you to look at the MATLAB script that I have posted to go along with this video lecture. The MATLAB script generates all the signals that you see on the right, and it shows how you can have MATLAB numerically calculate for you the Fourier transform values by approximating a complex domain Riemann integral based on the formula that we derived for the Fourier transform. So that script that I've posted, it gives you a tool that you can take any function x of t that you define and calculate its Fourier transform. And then there's code that plots the magnitude of the Fourier transform to help with visualization. So you can try changing the frequency. You can see what happens if you change to a sine instead of a cosine. You might want to try modifying the given code to plot the phase of the Fourier transform in addition to just its magnitude.